For starting any type of CFD calculations, we need some initial guess. The process of providing an initial guess is called initializing flow. All the variables being solved are required to be initialized or given an initial guess values. The more sensible the initial guess, better are the chances of quicker solution progress or convergence. Initial conditions are set for each physics continuum. Setting suitable initial conditions aid convergence of the flow solution. How to select a flow model in *CCM+? For this, we have to select a viscous regime model. To select a viscous regime in *CCM+, in the physics model selection dialog, select coupled flow model or segregated flow model. Then, in the viscous regime box, select the appropriate option by clicking the corresponding radio button. The physics model selection dialog shows the selected viscous regime model activated. When the gravitational acceleration and force are going to be predominant force for fluid flow, we need to include gravity effects in simulation. For this, there is the gravity model. The gravity model accounts for the action of gravitational acceleration in *CCM+ simulations. For fluids, it provides two effects. The working pressure becomes the piezometric pressure. The body force due to gravity can be included in the momentum equations. The gravity model also affects other types of simulations such as material particle flows under the Lagrangian multi-phase framework. To select the gravity model, first select the segregated flow model or select the coupled flow model. The gravity radio button becomes available for the selection under optional physics models. After you click the gravity radio button, the physics model selection dialog shows that the gravity model has been selected. When we talk about gravity, the effect of buoyancy comes into effect. Because density variations can occur due to temperature changes, the combined effect of gravity on density variations give rise to a variable force. A simulation with gravity should include such variations. For including this effect, a method called Boussines model is available. The Boussines model becomes available for selection when you use a single component gas or liquid and the gravity model is invoked with an energy model and the constant density model. This model provides a buoyancy source term that only applies when there are small variations of density due to temperature variations. The error introduced by the Boussines model can be estimated by comparing solutions where density depends on temperature with solutions where the density is constant, and the Boussines model is used. For the Boussines model, we have to specify a reference temperature and coefficient of bulk expansion within the reference conditions and material properties nodes of the physical continuum respectively. The Boussines model becomes available after you have selected the gravity model for a constant density flow. After solver and material properties models, we come back to boundary conditions. We will see what user inputs are required for each boundary conditions and how variables are internally calculated at different boundary condition types. First, let us see velocity inlets. For velocity, the inlet phase velocity vector is specified directly. For pressure, the boundary phase pressure is extrapolated from the adjacent cell using reconstruction gradients. For temperature, the inlet static temperature is specified. Now, let us see the symmetry plane boundary condition inputs. For velocity, the shear stress at a symmetry boundary is 0. The face value of velocity is computed by extrapolating the parallel component of velocity in the adjacent cell using reconstruction gradients. For pressure, the boundary phase pressure is extrapolated from the adjacent cell using reconstruction gradients. For temperature, the heat flux at a symmetry phase is 0. The face value of temperature is extrapolated from the adjacent cell using reconstruction gradients. What are the values required at wall? For velocity, for slip walls, the face value of velocity is computed by extrapolating the parallel component of velocity in the adjacent cell using reconstruction gradients. For no slip walls, the tangential velocity is explicitly set either to 0 or to a specified value. For pressure, the boundary phase pressure is extrapolated from the adjacent cell using reconstruction gradients. For temperature, for inviscid flow, the face value of temperature is extrapolated from the adjacent cell using reconstruction gradients. For viscous flows, either the temperature or the heat flux is specified. If the heat flux is specified, the wall boundary temperature is computed from the appropriate laminar or turbulent heat flux relationship. Let us see how calculations are made at pressure outlet condition. For velocity, the boundary phase velocity is extrapolated from the interior using reconstruction gradients. For pressure, when inflow occurs, the boundary pressure is assumed to be given by this relation. This approach discourages backflow from occurring. When outflow is there, for subsonic outflow, the boundary pressure is specified. For supersonic outflow, the boundary phase pressure is extrapolated from the adjacent cell value using reconstruction gradients.